Hello. This video is the first in a series introducing the topic of Twistor Theory, which is a subject first formulated by Roger Penrose in the late 1960s. Before I get into an introduction of the topic and writing down some of the definitions that will be useful, I should make a note about what I believe to be the prerequisites in order to follow this series. So, the two main prerequisites are the following. One is an advanced undergraduate knowledge of special relativity, and also a basic knowledge of differential geometry. So for special relativity, you should have some knowledge of Minkowski space, and you should have done some calculations in Minkowski space, or at least know how to do them. And for differential geometry, you should have a knowledge of smooth manifolds, so I'll call MFDs manifolds, and then also their tangent and cotangent bundles. I'll be defining smooth manifolds and their tangent and cotangent bundles below, just so that we all have the same notation. Moving on to just the goal of Twistor theory. The goal that we wish to accomplish in studying Twistor theory is having a better understanding of quantizing fields in spacetime. So ST here is spacetime. And this was the approach that Penrose took in studying Twistor theory. But there are more general applications besides this goal. So looking at some of the applications, they are threefold. So firstly, we have a purely mathematical application, and that is the subject of the Penrose transformation, which is something that we'll see later in this series. And the Penrose transformation is interesting for mathematicians because it has certain geometrical features and complex analytic features. But it also has applications in a more physical setting, specifically within quantum field theory, or QFT. So within QFT, it's interesting to study elementary particles and their interactions within Minkowski space. A recent program known as celestial holography uses exactly this. It uses Twistor theory to study interactions within Minkowski space. So that's another application of this theory. A third application is a far more modest one and a more pragmatic one, and that is Twistor theory is very useful in solving certain nonlinear equations. So if you're just interested in solving certain equations, Twistor theory can also be of use. So, assuming any of these seem interesting to you, we can begin just by writing some definitions that will be very useful within this series. So to start, we want to define a manifold, and in order to do that, we have to build up some structure. So, defining an atlas, we begin as follows. Let M be a set. Then, a CRN subatlas on M is a collection of pairs of the form phi h and UH, where UH is a subset of M. So, a CR subatlas is a collection of subsets of M along with maps, which are labeled phi h, which are 1-to-1, and they map U to an open subset of Rn. So a CRN subatlas is just a collection of maps and subsets of M. Those maps map these subsets of M onto the real numbers, onto Rn. So a maximal collection, so maximal here means that we can't add any more pairs to this collection and get new information. So assuming we have a maximal collection of CR related pairs, that maximal collection is called the CRn atlas. So this is the definition of an atlas that you may have seen from differential geometry before. And as a note, when I write CR related pairs, related simply means that given two pairs in this subatlas, so phi u and psi v, these two pairs are related if the maps phi composed with psi inverse and the map psi composed with phi inverse are both CR maps. And here, CR means that the functions, so phi h, so here CR means phi h is R times differentiable. So R times differentiable means that you can take R derivatives of phi h and you still have a continuous function. After R times, you may no longer have a continuous function. And you may have seen this within the context of a C infinite function. So you may have seen this written as a C infinite function. And C infinite functions are infinitely differentiable. So for example, e to the x is infinitely differentiable. You can take as many derivatives with respect to x as you'd like, and you still get a continuous function. So with the definition of an atlas now known, we can define what a manifold is. So an n-dimensional CR manifold, or what I'll call a CRn manifold, written here. So MFD I will write for manifold. So a CRn manifold is a set M together with a CRn atlas. So we just have a set M, and with M we have this CRn atlas, which is just this maximal collection of maps and subsets of M. So for some specifications here, when R is equal to 0, M is called a locally Euclidean or topological manifold. However, when R is not equal to 0, M is a differentiable manifold or a smooth manifold. We'll be more interested, at least physically, with smooth manifolds. And as a quick note about definitions, an atlas on a set M is often called a differentiable structure or a manifold structure. So when we say a set M has some differentiable structure, that differentiable structure is really a CRn atlas, as we had defined above. Next, I will define tangent and cotangent bundles on manifolds, just so that we all are using the same notation here. So let M be a C infinite n manifold. So it's an n manifold where the coordinate maps phi are C infinite, where they're infinitely differentiable. And to find the following set, we let Tm be the set of pairs M and X such that M is in the set M, or M is a point on the manifold, and X, big X, is a vector or an element of the tangent space of the manifold M at point M. So the tangent space, as seen here, is given, let's say, given some arbitrary manifold, let's say a sphere, and a point on the manifold M, the tangent space T little m m is the space of all vectors that are tangent to the manifold at that point. So here, since M is a two-dimensional surface, the surface of a sphere, the tangent space TMM is given by it's spanned by two vectors. So it's a plane which contains all of the vectors parallel to the manifold M. So Tm is just the collection of all of the tangent spaces. And this is actually the tangent bundle. But in order to describe it as the tangent bundle, we need to have maps as well. So we need to have some differentiable structure. And below, I'll be defining that differentiable structure, just for completeness. So let us also define a map, pi, which is a projection. So it takes an element of the tangent bundle, Tm, so that some element mx, and it projects it onto the manifold. So it takes some tangent space, and it projects it, or it takes some element of the tangent bundle, and it projects it onto the manifold. So just the point that vector x is at on the manifold. So we forget about x altogether, and we just remember m. Next, if phi u is a coordinate pair on M with coordinates given by xi is equal to ui composed with phi, where here ui is just a projector. So ui is specifically called a natural coordinate function. So it takes an element of Rn, which is given by this vector a1, a2, all the way up to an, and it gives us the ith component. So given the composition of ui with phi, and defining u bar to be the pre-image of u, so it's defined to be the fiber of u, then we also define xi bar, which is given by xi composed with pi. So far we have two maps that we've defined. That is xi, which is the composition of ui and phi, and also xi bar, which is just the composition of xi with the projector map. And for some element mx in u bar, because we know u here, u is a subset of m. So if we take the pre-image of u with respect to the map pi, we should get an element, or we should get a set of elements in the tangent bundle Tm. So taking some element of u bar, we have mx in u bar, where mx is some element of the tangent bundle. We let xi bar acting on mx is equal to ai, assuming that x, the vector, is written in the standard basis of tangent planes. So this tangent space here. So we have that dxi. This is given as the standard basis of the tangent plane, or the tangent space. And assuming we can write, so we can also just write this as some coordinate basis. So in linear algebra notation, we can write it as ei hat. So it's just some basis. Then ai are the coefficients of this basis. And all that we've said above is that we're defining some map xi bar, which gives us the coefficient of the ith basis for the vector x. So that is exactly what a coordinate function does. And I'll explain why this xi map gives us ai. So the reason is that we're feeding into xi bar mx, an element of the tangent bundle. But we've defined xi bar to be xi composed with pi. Then we know that pi projects mx onto m. So we have now xi acting on m, but we've defined xi to be ui composed with phi. Then phi, what does phi do? Phi takes, so I'll write it here, phi is a map from ui, so phi is a map from u, some subset of the manifold M, and we map it onto Rn. So we just say, let phi m be some vector in Rn. Here we'll write it as a1 all the way up to an. Then ui, little ui acting on this vector, we defined it as being the projector onto the ith element. So we see that xi hat acting on mx is equal to ai. It gives us the ith component, or the ith coefficient of the basis expansion of the vector x. So as a more down-to-earth example, a coordinate function for, say, the vector v is equal to x hat plus 3y minus 8z should give us the following. Well, if we ask for fx acting on v, where f is the coordinate function, we want it to give us the coefficient in front of x hat. The coefficient in front of x hat is 1, so we wish for fx to give us 1. Fy should give us the coefficient in front of y hat, which is 3. So Fy acting on v should give us 3. And Fz acting on v should give us the coefficient in front of z hat, which here is negative 8. So given a basis, which we already have for the manifold, which is d dxi, in order to completely specify some vector that we're talking about, all we need is the AIs. And the way that we do that is, given this double mx, we act on it with xi hat, and it gives us the coefficient. So xi hat really is a coordinate function for elements of the tangent bundle, which is exactly what we were searching for. So let now phi hat be a map. So phi hat here is a map from u hat, which again is the pre-image of u, and it maps to r to the 2n, where here we have 2n because of the following. So we define phi hat by, when we compose ui here with phi hat, then we get xi hat. So this is the coordinates that we just defined above. And if we take, so this is for I is equal to 1 all the way up to n. And so that's for the first n elements. But because we're mapping to r to the 2n, we have to consider the second n elements. So the second n elements, again, if I is equal to 1 all the way up to n, then u sub n plus I gives us the second n components. And when we compose these second n components with phi bar, we get xi, which were the original coordinates that we had defined. So recall xi is equal to ui composed with phi. So these were the first n these were the first n coordinates that we had defined above. So now this phi bar gives us 2n coordinates. It gives us the first n coordinates that we had constructed, and these are coordinates on M, and the second n, or the other n components of phi bar, give us the new coordinates that we had constructed, which are coordinates on Tm. So it can be shown that the subatlas of pairs given by phi bar u bar defines a C-infinite structure on Tm. And with this structure, Tm is the tangent bundle of M. So now that we've defined the tangent bundle on M, we can move on to defining the cotangent bundle on M, which has a similar definition. So going to this definition, we have that for a set T star M given by the following. So it's given by the pairs of MW such that M is in the manifold M, so it's some point on the manifold, and W is an element of the cotangent space at the point M. So again, the cotangent space is the space of all linear functionals which send elements of TMM to the real numbers. So to be specific, for an element V in the tangent space at M, there exists an element W of the cotangent space such that W acting on V is an element of the real numbers. Or if we have some more general field, this could be like if our field is the complex numbers, this could be an element of the complex numbers. Or more generally, for a field K, W acting on V is an element of K. But given this set, together with the projector pi, which projects from this set T star M onto M, so as before, we take an element of T star M, which is given by MW, and we just forget about W. We just project onto the point on the manifold M. Given these two things, we let x1 up to xn be a coordinate system on M with domain given by U. So x1 up to xn are valid on this subset U of M. So U is a subset of M. We define the next functions. We define Q1 up to Qn and P1 up to Pn. And these are defined on the preimage of U. So these are defined on T star M, and they are defined as, well, Qj is defined to be xj, the coordinate system, one of the coordinate functions on M, composed with pi. And Pj is defined as the coefficients of W. So here W is the covector, or the element of the cotangent space, which is called a covector. So Pj are the coefficients of the covector in question, where here dxj is the dual basis to dxj. So what I mean here is that what I mean here is that del xj acting on dxi is equal to delta ij. So it's equal to the Kronecker delta. With these two n coordinate functions, t star m, the set that we were concerned with, is a C infinite 2n manifold. And it's called the cotangent bundle of M. So here the cotangent bundle of M is just this set, T star M, together with these two n coordinate functions. And as a note, the reason that we have two n coordinate functions, so before when we were defining tangent bundles, we mapped to r to the 2n. And so we mapped r to the 2n here for our function phi bar. And the reason that we did that is because t star m and tm both consist of pairs of two things. They consist of a pair. The first is m. M is a point on the n-dimensional manifold. So you need n numbers to describe M. And then we have W. For the case of Tm, we had this big X here. But in either case, X is an element of the tangent space at M. And we know that the dimension of the tangent space and the dimension of the cotangent space are both the dimension of M. So here we need another n numbers to define W. Here, those n numbers are given by the pj's. And the qj's help us to define M. So the reason that we have qj and pj is that qj helps us to define M entirely, and then pj helps us to define W entirely. So that's why we have two n coordinate functions, because the tangent bundle and the cotangent bundle are two n-dimensional spaces. They're two n-dimensional manifolds even. And moving on, the fundamental one form, W on M, is given by the following map. It's given by pi pullback W. So I'll now define what the fundamental one form is and what the pullback is, what this star notation actually means. So on the left, we'll define what the fundamental one form is. So on the left, the fundamental one form is just the induced metric on the space Tp star M, where P is a point on the manifold. So here, P is an element of M. And an induced metric, G induced at the point P, is just a generalization of the inner product. So in a linear space, a linear vector space, we have an inner product of two vectors. Here on a manifold, you can't quite define an inner product on two vectors at different points. So what you do is you define a metric, G, which at a point P can define an inner product of two elements of the tangent spaces. So what I mean is that given a sphere, let's say, and a point on that sphere, let's say 2 points. So this is point P, P1, and this is point P2. Well, these points have their own tangent spaces. These points have their own tangent spaces, given here. But it makes no sense for a vector at P1 to be related to a vector at P2 because they're not in the same vector spaces. So TP1M is its own vector space, and TP2M is also its own vector space, where the sphere is the manifold M. But you can only take the inner product of two vectors within the same vector space. So what the metric does is the metric says at a point P, let's say P1, we can take the inner product of two vectors at that point. And then we generalize G to all the points on the metric M. So the induced metric is just the metric at a specific point. Here it would be at point M. So that's what the fundamental one form is. It's just this GP object. And the pullback is the following. So for a map, which takes us from a space V to a space W, for that map, we actually induce another map, which is F star, and it maps from W star to V star, where here the stars on the spaces simply mean the dual spaces, or the spaces of dual vectors. And F star is defined by the following. We define F star to be, it's a map from G, which is an element of W star, and it maps it to H, which is an element of V star. And the way we define H is we say it's F star G, which is also written in this way, and it's just defined as this. It's the precomposition of F with G. So for us, here, W, the fundamental one form, is the pullback of pi acting on W. So here, that would be defined by W composed with pi. So that is what the pullback really is here. And that ends this first video introducing twistor theory and some of the definitions that we'll be using extensively. This may have been quick, but this was really just a way to brush up on topics that you should already know and be familiar with. I was just writing my own notation that I'll be using throughout this series so everybody's on the same page. In the next video, we'll be reviewing some tensor algebra and tensor calculus, and we'll also be writing down some definitions of bundles. So here I've been saying that Tm is a tangent bundle and T star m is a cotangent bundle. So I'll be defining exactly what a bundle is in the next video, and also reminding you of some tensor algebra and calculus that will be very useful throughout the rest of this series. So thank you very much.